Hi everyone, Dr. J here, and in this video I want to emphasize a little bit more a few things about covariance and correlation that are going to be important for us in the rest of this class. So covariance is very similar to variance, and we've seen in other videos that variance can be written as expected values of something. So just to give a little review, if we have a random variable, let's call that x, and this random variable could be anything. It could be the value of a dice roll. It could be the value drawn from a Gaussian distribution. It could be the number of chocolate chip cookies in a cookie. Okay, so it could be anything. Random variable x. The average, or the mean, is defined as the expected value of x, where I'm using the E, capital E, as expected value, and then the brackets denote that there's a random variable inside there, and then mu is our Greek symbol, mu, for the mean. So the expected value of x is the mean. The variance of x, let's write it this way, it's the expected value, and then we'll put something in these brackets here. And again, just as a reminder, the expected value, it's what you expect, right? So if you take a weighted average of all the values in x, weighted by their probabilities, and then integrate or sum, depending on if it's a discrete or continuous random variable, you'll get the mean. So it's like you're weighting all the possible values you could get in x by the probabilities of getting those values, and so it's the center of your data set. It's the average. Same thing here with variance, except now it's the expected value of x minus mu squared. X minus mu. So take x and remove its mean. So in the case of, let's say, the sum of a pair of two dice, we take the two dice, every time we roll it, we subtract off the value of the average, the expected value, or the average sum of that roll of pair of dice, and then we take the difference and square it. So a couple of things. X minus mu, it's like a distribution that's been normalized by its mean, so it is the average is now 0. X minus mu is setting the average to 0, and then squaring means that we're getting all positive numbers. So the expected value of x minus mu squared is the variance. Now the covariance is very, very similar to the variance, but now inside brackets we don't just have one variable, we have two. So there are two variables for a covariance, right? We're asking the question, how does one random variable y covary with a random variable x? And if we just look at the variance, we can actually almost directly figure out what that is. It's the expected value, and now we have to distinguish between the mean of x and the mean of y. It's the covariance of x and y is equal to the expected value of x minus the mean of x times y minus the mean of y. Okay? So we have expected value, the variance is the expected value of x minus its mean squared, and here instead of x minus its mean times x minus its mean, we have x minus its mean times y minus its mean, is the definition of the covariance. And, you know, because of the fact, again, the expectation operator is a linear operator, we could actually multiply this out, and so we would have that this is going to equal something, something else. So let's go ahead and do that, actually. Alright, so let's just work out what this would be. So we have covariance of x and y is equal to the expected value of x minus mu x times y minus mu y. So we can write this as expected value. Alright, so we've just written out this top expression, in other words, expanded the parentheses. Expected by x times mu x, or sorry, x minus mu x times y minus mu y is equal to x times y minus mu xy minus mu yx plus mu yux. Now there's a number of properties of these expectation operators. One of those properties is that the expectation of a constant is just the constant itself, and because the mean is a constant, we can actually take those out. And remember also that the other property of expectation operators is that they're linear, so the expectation of a plus b is equal to the expectation of a plus the expectation of b. Alright, so there we've kind of expanded this out. And now we have expected value of x times y minus mu x times the expected value of y minus mu y times the expected value of x plus mu y mu x. So now we note that expected value of y is just mu y, expected value of x is just mu x, so we've got minus 2 mu x mu y, minus mu x mu y minus mu y mu x plus mu y mu x. So one of these guys is going to cancel out, and then we'll just be left with 1. So we have equals to the expectation of x times y minus mu x mu y. So that's the another way to write the covariance of x and y. It's the expected value of x times y minus mu x mu y, or the expected value of x times the expected value of y. Now, for starters, just notice for a second that if we say the variance, so if y equals x, so covariance of x and x is equal to the variance of x, then we have the expected value here of x squared minus the mean of x squared, and that is the standard definition of the variance. Also notice that we have this very important property here, the expected value of x times y. Now, one of the definition actually of independent random variables, is that the expected value of x times y is equal to the expected value of x times the expected value of y. So this is the definition of independence, statistical independence of two random variables. And of course that is the mean of x times the mean of y. So if we have two variables that are independent, then their covariance is going to equal 0 by definition. So for independent variables, their covariance is 0. However, that does not mean that two variables for which the covariance is equal to 0 are independent. For example, alright, so we'll leave that there for the moment. Let's say we have two variables, x and y, and we have x is a Gaussian and y is equal to x squared. So all of the points, y is a random variable, by the way, so a random variable can be a function of another random variable, but in this case it's a completely deterministic function, y equals x squared, and so actually even though the two variables are completely deterministically dependent, so you know what x is, you can exactly tell what y is, that's complete dependence, they're actually, the covariance between these two variables is going to be 0. And the reason for that is that there's no way we can fit a line. Remember, I've said this before, that covariance and correlation are going to be related, or as they're described in the book, are for linearly related variables. So there's no linear relationship between x and y here, because it's a quadratic. It's y equals x squared. And so even though two variables may not be correlated at all in terms of their correlation coefficient, they may have a covariance that's equal to 0 just because of the mathematical definition. That does not mean that they're not dependent variables. So that's something to keep in mind. Okay, so now how about correlation? So we've talked about covariance, how one variable covaries with another variable, and that's, by the way, going to be important when we come to talking about variograms, and we'll actually be trying to estimate how variables vary with other variables. But let's also talk about correlation, and so we can define a correlation coefficient, rho, and sometimes this is also called the Pearson's correlation coefficient, and this is equal to the covariance of x and y divided by the variance of x times the variance of y. So this is just the covariance that's normalized by the variances of those two random variables. And this has the property that it essentially varies between between -1 and 1. So Two variables that have a correlation coefficient of -1 means they're negatively correlated. Perfectly negatively correlated. Positive one would be perfectly positively correlated, so when one variable goes up, the other variable goes up. And a correlation coefficient of 0 is again non-correlated, but non-linearly correlated, as we've already said. So one drawback that the book points out about the correlation coefficient is that it's not very robust to outliers. So if you have outliers in the data, then your correlation coefficient could be very low, even though most of the data is actually matching that quite well. And so there are other types of robust estimators of correlation which remove the effect of outliers. And we may or may not talk about those in this class, probably not, but if you need help with something like that for your projects, then you can come and talk to me. Okay, so with that, I will wrap up this short video on correlation and covariance, and I'll see you in the next video.